Let's get ready to explore. Number 10. The Fermi Bubbles. In November 2010, astronomers using NASA's Fermi Gamma Ray Space Telescope made a discovery so unexpected that the lead researcher Douglas Finkbeiner of the Harvard-Smithsonian Center for Astrophysics reportedly said it just confuses everything. Extending above and below the center of our own Milky Way galaxy were two colossal structures, each stretching 25,000 light-years from the galactic core. They had been there for millions of years. Nobody knew. The Milky Way is our home galaxy, a system we have been mapping and studying for centuries. By 2010, astronomers believed they had a reasonably solid picture of its large-scale structure, a spinning disk of stars, gas, and dust with a supermassive black hole at the center. The idea that two galaxy-sized energy structures were looming above and below that disk, completely undetected, seemed almost impossible. These structures, now called the Fermi Bubbles, emit high-energy gamma radiation, the most energetic form of light in the universe. They are expanding outward at approximately 2.2 million miles per hour, and the total energy contained within them is equivalent to roughly 100,000 supernova explosions. Their edges are razor-sharp, almost geometric in their precision, which suggests they were created by a single catastrophic event, rather than any gradual process. The leading theory connects them to Sagittarius A star, the supermassive black hole at the Milky Way's center. Perhaps a few million years ago, that black hole consumed an enormous amount of matter and released a titanic burst of energy that inflated these structures over tens of thousands of years. A competing theory argues that an intense period of star formation near the galactic center drove the bubbles outward through stellar winds and supernova pressure. Neither explanation has fully convinced the scientific community, and the debate remains active today. The Fermi Bubbles are a humbling reminder that even the galaxy we live inside is still capable of hiding enormous secrets from us. If structures this massive could go undetected until 2010, what other colossal features of our own galaxy are we still missing? Number 9. The Boötes Void. In 1981, astronomer Robert Kirshner and his team at the University of Michigan were mapping the large-scale structure of the universe when they discovered something that should not exist. In the direction of the constellation Boötes, they found a region of space nearly 330 million light-years in diameter that contained almost nothing at all. No galaxies, no clusters, almost no matter of any kind. Just an enormous, near-perfect sphere of emptiness sitting in the fabric of the cosmos. The universe, on its largest scales, has a recognizable structure. Galaxies cluster along vast filaments and walls of matter, like foam on the surface of an ocean, with voids between them. These voids are expected. They are a natural consequence of how gravity pulls matter together over billions of years. But those voids are typically irregular in shape, limited in size, and still contain scattered galaxies throughout. The Boötes Void was different in every respect. Where astronomers expected to find thousands of galaxies, they detected roughly 60. The void's diameter of 330 million light-years makes it one of the largest known structures in the observable universe, and its near-perfect spherical geometry has no satisfying natural explanation. Natural cosmic structures, sculpted by the complex interplay of gravity and expansion, are irregular and uneven. The Boötes Void's almost artificial symmetry is deeply strange. Standard cosmological models struggle to account for something this empty and this large. Some researchers have proposed it formed through the gradual merging of smaller voids over billions of years. Others suggest density fluctuations in the very early universe seeded this region differently from its surroundings. But these explanations fail to account for both the void's extreme size and its astonishing emptiness simultaneously. No single mechanism explains both features at once. The Boötes Void stands as one of astronomy's most persistent structural enigmas. If our entire Milky Way galaxy were placed at its center, our most powerful telescopes would detect no other galaxies in any direction, It is the closest thing to true nothingness that the universe has ever produced, and we still cannot explain why it exists. Number 8. Magnetars. On December 27th, 2004, more than a dozen spacecraft in orbit around Earth and scattered across the solar system were simultaneously overwhelmed by the most intense burst of radiation ever recorded from beyond our solar system. The source was an object called SGR 1806-20, located approximately 50,000 light-years away on the far side of the Milky Way. In 0.2 of a second, it released more energy than our Sun will produce in 250,000 years. The burst was so powerful, it disrupted Earth's ionosphere from halfway across the galaxy. SGR 1806-20 is a magnetar, a type of neutron star with a magnetic field exceeding 10 to the power of 15 Gauss, more than a quadrillion times stronger than Earth's own magnetic field, and roughly 1,000 times stronger than an ordinary neutron star. Magnetars are already among the strangest objects in the known universe, packing roughly the mass of our entire Sun into a sphere approximately 20 kilometers across. Their surface gravity is approximately 200 billion times that of Earth. What makes magnetars genuinely impossible seeming is the origin of their magnetic fields. No known stellar process should be capable of generating fields this extreme. When a star collapses into a neutron star at the end of its life, the resulting magnetic amplification should produce powerful fields, but not fields of this magnitude. The mechanism that creates magnetar-strength magnetism remains one of astrophysics' most stubborn unsolved problems, and the 2004 burst from SGR 1806-20 demonstrated the consequences with terrifying clarity. The December 2004 event, caused by a starquake on SGR 1806-20's surface, released a shockwave of gamma rays and X-rays that changed the ionization density of Earth's upper atmosphere by up to 6 orders of magnitude, according to research published in the Geophysical Journal International. Victoria Caspi of McGill University, one of the leading magnetar researchers in the world, has noted that magnetars are the only deep space objects ever observed to directly affect Earth. The burst briefly shifted our ionosphere from a nighttime state to a daytime state in a fraction of a second. If a magnetar of this type were located within 10 light-years of Earth, the resulting burst would be capable of devastating our atmosphere and potentially triggering a mass extinction event. The nearest known magnetar sits roughly 9,000 light-years away. That distance feels significant, until you remember that 50,000 light-years was not nearly far enough to prevent SGR 1806-20 from reaching out and touching our planet. Number 7. Quasi-stars. In a series of theoretical papers published between 2006 and 2008, astrophysicists Mitchell Beagelman, Marta Voluntari, and Martin Rees described a type of object that the laws of physics technically permit, but that strains those laws almost to the point of breaking. They called them quasi-stars. Colossal, stellar structures, potentially containing billions of times the mass of our Sun. Powered not by nuclear fusion like ordinary stars, but by a black hole embedded within them, consuming matter from the inside out. To understand why quasi-stars matter, you need to understand a problem that has troubled cosmologists for decades. Observations of the early universe reveal supermassive black holes, billions of times the mass of our Sun, already fully formed just a few 100 million years after the Big Bang. This is a serious problem. Standard models of black hole growth through ordinary matter accretion cannot produce objects that massive in that short a time. Something extraordinary must have seeded them. Quasi-stars are the most compelling theoretical answer. A quasi-star, in theory, would form when the core of a massive primordial gas cloud collapses directly into a black hole of perhaps 1,000 to 10,000 solar masses, but the surrounding envelope of gas is so vast that it cannot escape. Instead of exploding outward as a supernova, The material becomes a quasi-stellar envelope, with the interior black hole consuming it steadily. The resulting structure could reach estimated masses of up to 10 billion times that of our Sun, dwarfing any known stellar object by an extraordinary margin. No quasi-star has ever been directly observed. They are believed to have existed only in the very early universe, within the first billion years after the Big Bang, before being consumed by their own internal black holes. Their surface temperatures would have been far cooler than ordinary stars, making them relatively dim for their size, which helps explain why we have not found direct evidence of them. Astronomers are currently searching early universe data from the James Webb Space Telescope for potential signatures of these objects. Quasi-stars represent a peculiar kind of scientific impossibility, an object that exists precisely at the edge of what the laws of physics allow, invented not from speculation, but from necessity. We needed them to explain something we had already observed, and the explanation turned out to be barely more possible than the problem it was meant to solve. Number 6. Pulsars. On November 28, 1967, Cambridge postgraduate student Jocelyn Bell was reviewing paper chart recordings from the Mullard Radio Astronomy Observatory's newly built radio telescope when she noticed something she could not explain. From a fixed point in the constellation, Vulpecula came a radio signal pulsing with extraordinary regularity, once every 1.3373 seconds, with a precision that rivaled the best atomic clocks on Earth. Her supervisor, Anthony Hewish, was so baffled by the signal's mechanical perfection that the two researchers half-jokingly labeled it LGM-1, Little Green Men 1. The interplanetary scintillation array that Bell had helped construct was designed to study quasars, distant and well-understood radio sources. Regular, repeating signals from space had no place in the existing catalog of known phenomena. No natural object, astronomers believed at the time, should be capable of producing a pulsed radio signal with that degree of clockwork regularity. The universe, in their understanding, was not that precise. What Bell had discovered was a pulsar, a rapidly rotating neutron star that sweeps a beam of electromagnetic radiation across the sky like a cosmic lighthouse. The object itself, designated CP 1919 and later PSRB 1919 plus 21, is composed of matter compressed to nuclear density, roughly 1.4 times the mass of our Sun, crushed into a sphere approximately 20 kilometers across, 400 trillion times denser than water. Its crust is approximately 10 billion times stronger than steel. Neutron stars exist in a physical regime where the laws governing ordinary atomic matter cease to apply. At nuclear density, protons and electrons are crushed together into neutrons, creating a state of matter that cannot be replicated in any laboratory on Earth. Some pulsars spin faster than 700 times per second. The most stable millisecond pulsars keep time with a precision that surpasses human-built atomic clocks. Yet our theoretical models of what is actually happening inside a neutron star remain incomplete. Physicists still cannot agree on a definitive equation of state for their interiors. Inside every pulsar is a form of matter that no experiment has ever directly sampled, obeying rules that no physicist has fully written down, spinning at speeds that would tear apart any ordinary structure in the universe. We have detected thousands of them. We still cannot fully explain what they are made of. Number 5. The cosmic cold spot. In the first year of data returned by NASA's Wilkinson Microwave Anisotropy Probe, a team of researchers analyzing the cosmic microwave background noticed something anomalous in the southern sky. In the direction of the constellation Eridanus, there was a region approximately 70 microkelvin colder than the surrounding cosmic background. A figure that sounds small but represents a deviation so extreme that the probability of it occurring by chance is estimated at less than 2%. It was later confirmed by the European Space Agency's Planck satellite in 2013. Cosmologists called it the cold spot, and it has unsettled them ever since. The cosmic microwave background is the oldest light in the universe, the faint thermal afterglow of the Big Bang itself, dating to roughly 380,000 years after the universe began. It fills the entire sky with near-perfect uniformity. The tiny temperature fluctuations within it, typically no more than 18 microkelvin in either direction, encode the seeds of every galaxy, every star, and every structure that would ever form. The cold spot is not a tiny fluctuation. It is a vast, anomalous scar in the oldest light we can observe. In 2015, a team led by Istvan Sapudi of the University of Hawaii's Institute for Astronomy identified a supervoid in the direction of Eridanus approximately 1.8 billion light-years wide, centered roughly 2 billion light-years from Earth, that appears to coincide with the cold spot's location. This supervoid, confirmed with high confidence by the Dark Energy Survey in December 2021, could theoretically chill CMB photons passing through it via a mechanism called the integrated Sachs-Wolf effect. But here is the problem. Even this enormous void accounts for only about 10 to 20% of the observed temperature deficit. Something else is responsible for the rest. The remaining temperature anomaly has generated several competing explanations. A 2007 paper by researchers Cruz and colleagues suggested the cold spot could be a remnant of a cosmic texture, a defect left over from a phase transition in the very early universe. The most provocative hypothesis comes from cosmologist Laura Mersini Houghton, who proposed that the cold spot is a bruise left in our universe by a collision with a neighboring parallel universe before the two were separated by cosmic inflation. The cold spot may be the oldest unsolved mystery in observational cosmology, a wound in the universe's earliest light whose cause no current theory fully explains. It sits there in the southern sky, colder than it has any right to be, a billion light-years wide, waiting for an answer that has not yet arrived. Number 4. White holes. Einstein's field equations of general relativity are among the most tested and confirmed mathematical descriptions of reality ever produced. They predicted black holes before any had been observed, described gravitational waves decades before their detection, and have passed every experimental test physicists have thrown at them for over a century. But buried within those same equations, with the same mathematical inevitability as black holes, is a second type of object that has never been observed, cannot be approached, and expels matter and energy so violently that nothing in the universe could ever enter it. Physics calls it a white hole, and the equations do not merely suggest it exists. They insist on it. A white hole is the precise time reversal of a black hole, where a black hole draws everything inward beyond an event horizon from which nothing escapes. A white hole repels everything outward from a horizon that nothing can penetrate from the outside. The mathematics describing both objects emerges from the same Schwarzschild solution to Einstein's equations, published in 1916. The black hole half of that solution became one of the most studied phenomena in modern astrophysics. The white hole half was largely set aside, considered an unphysical curiosity, a mathematical artifact that the real universe would never actually produce. That dismissal may have been premature. In a series of papers published between 2014 and 2018, physicist Carlo Rovelli and collaborators at Aix-Marseille University proposed that black holes, through a process governed by quantum gravity, do not simply evaporate as Stephen Hawking suggested in 1974. Instead, they argued, a black hole at the end of its life undergoes a quantum bounce and reemerges as a white hole, explosively releasing all the matter and energy it ever absorbed. Some researchers have further speculated that certain fast radio bursts, those millisecond flashes of intense radio energy from deep space, could represent the final dying explosions of ancient, microscopic white holes. General relativity places no prohibition on white holes. They do not violate energy conservation. They do not break causality. They emerge naturally from the equations without being artificially inserted. The reason physicists have struggled to accept them is essentially observational. We have never detected one. But absence of evidence is not evidence of absence, particularly for objects that, by their very nature, repel any probe or instrument that might try to approach them. Einstein's equations have never been wrong about a prediction of this kind. They told us gravitational waves existed, and we found them. They told us black holes existed, and we found them. They tell us white holes exist, and we have found nothing. That silence is either the most significant gap in observational astronomy or the universe's most persistent refusal to show us one of its own rules. Number 3. The JWST early galaxies. On December 25th, 2021, the James Webb Space Telescope launched from the Guyana Space Center in Kourou, French Guiana, and began its journey to a gravitational balance point 1.5 million kilometers from Earth. Within months of beginning operations, it started returning images that cosmologists described in published scientific papers as deeply troubling. Fully formed, massive galaxies were appearing in JWST's data from a period only 300 to 700 million years after the Big Bang, a time when the standard model of cosmology said such objects had no business existing at all. The lambda CDM model, which stands for lambda cold dark matter, is the framework that modern cosmology uses to describe how the universe evolves from the Big Bang to the present day. It has been spectacularly successful, accurately predicting the distribution of galaxies, the structure of the cosmic microwave background, and the large-scale architecture of the cosmos. According to that model, galaxies grow slowly, assembling from smaller structures over billions of years. In the first few 100 million years after the Big Bang, the universe was supposed to be too smooth, too young, and too underdeveloped to have produced anything resembling a mature, massive galaxy. JWST found 6 galaxies, identified by astronomer Erica June Nelson of the University of Colorado Boulder in the telescope's very first deep images, each appearing to exist within the first 500 to 700 million years of cosmic time, each carrying a stellar mass of at least 10 billion times the mass of our Sun. One appeared to rival the Milky Way in total mass, despite the fact that our galaxy had billions of additional years to form and grow. In 2022, Michael Boylan Colchin of the University of Texas at Austin posted a formal analysis that was subsequently published in Nature Astronomy, concluding that the most massive of these candidates lie at the very edge of what lambda CDM mathematically permits, suggesting a fundamental unresolved tension with standard cosmology. Subsequent research has provided some partial explanations. Some of the most extreme candidates were later revised downward in estimated mass. Astronomers have proposed that early star formation may have been far more efficient than current models assume, converting nearly all available gas into stars rather than the 10% typical in the modern universe. Others have suggested that early dark energy, a modified version of the cosmological constant that would have been stronger in the infant universe, might have accelerated structure formation beyond what standard models predict. None of these solutions has achieved consensus. The James Webb Space Telescope was built, in part, to look back at the universe's earliest chapters and confirm the story we thought we already knew. Instead, every deep image it returns shows a universe that assembled itself faster, more efficiently, and on a larger scale than any model predicted. The story is not confirmed. It is being rewritten. Number 2. Rotating black holes and the Penrose process. In 1969, Oxford mathematician Roger Penrose published a paper describing a consequence of rotating black holes so strange that it seemed to undermine one of physics' most fundamental principles. He demonstrated that a rotating black hole must possess a region outside its event horizon, a zone called the ergosphere, where the fabric of space-time itself is dragged around the black hole, like water circling a drain. Within this region, he proved, an object could split apart, with one fragment falling into the black hole, while the other escapes carrying more energy than the original object brought in. The black hole itself would slow slightly, surrendering rotational energy to the escaping fragment. In other words, a rotating black hole is an extractable energy source, and the universe's own geometry makes the extraction possible. This result, now called the Penrose process, was not a theoretical curiosity. In 1963, mathematician Roy Kerr had already published an exact solution to Einstein's field equations describing the space-time geometry around a rotating black hole. That solution, the Kerr metric, is now understood to describe nearly every black hole in the universe, since virtually all black holes inherit angular momentum from the material that formed them. The ergosphere and its strange properties follow inevitably from Kerr's mathematics, the same mathematics that has been confirmed by gravitational wave detections and the direct imaging of black holes by the Event Horizon Telescope. In 1977, Roger Blanford and Roman Znajek extended Penrose's work to show that magnetic fields threading the ergosphere of a rotating black hole could act as an electromagnetic version of the Penrose process, extracting rotational energy in the form of massive relativistic jets of particles. This Blanford-Znajek mechanism is now considered the leading explanation for the colossal jets observed shooting from the cores of active galaxies, including the famous jet from M87 star, the black hole imaged by the Event Horizon Telescope in 2019. The strange geometry Penrose described in 1969 is, apparently, one of the most powerful energy sources in the observable universe. But Penrose's work contains a darker implication. General relativity includes what physicists call cosmic censorship, an unproven conjecture proposed by Penrose himself, which holds that singularities, the points where density becomes infinite and physics breaks down, must always be hidden behind an event horizon, shielded from the rest of the universe. A black hole spinning at the theoretical maximum permitted by the Kerr metric would have an event horizon that shrinks to a ring, and exceeding that maximum would expose the singularity directly. A naked singularity would be a point in the universe where physics simply stops working, visible to everything around it, unshielded, and without any known remedy. Cosmic censorship has never been mathematically proven. Some numerical simulations suggest it can be violated under specific conditions. Roger Penrose received the Nobel Prize in Physics in 2020 for proving that black holes must exist as a general consequence of general relativity. Inside the same mathematics that earned him that prize is an object so extreme that its existence would mean the equations that predicted it cease to be valid. Physics wrote a rule that, under the right conditions, physics itself cannot enforce. Number 1. Dark energy. In 1998, two rival teams of astronomers set out to measure one of the universe's most fundamental properties, the rate at which gravity was slowing the expansion of the cosmos. The High Z Supernova Search Team, led by Brian Schmidt, with crucial contributions from Adam Rees, and the Supernova Cosmology Project, led by Saul Perlmutter, were competing to use distant Type 1 A supernovae as cosmic distance markers precise enough to measure the universe's deceleration. Both teams checked and rechecked their data for months. Both arrived at the same result. The universe was not decelerating. It was accelerating. Something unknown was pushing everything apart with increasing force, and that force was growing stronger as the universe expanded. Perlmutter, Schmidt, and Rees would receive the Nobel Prize in Physics in 2011 for a discovery that remains, to this day, one of the most profound and unanswered questions in all of science. Whatever is causing this acceleration has been named dark energy. It comprises approximately 68% of the total energy content of the observable universe, far exceeding ordinary matter at roughly 5% and dark matter at approximately 27%. Dark energy does not cluster. It does not interact with light. It does not form structures. It appears to be perfectly uniform, filling all of space with a constant density that neither increases nor decreases as the universe expands. It is the dominant component of everything that exists, and we have no confirmed understanding of what it is. The most natural explanation, and the one embedded in the standard cosmological model, is that dark energy is vacuum energy, the energy of empty space itself, arising from quantum field theory's prediction that even a perfect vacuum seethes with fluctuating virtual particles. Einstein originally introduced a related term, the cosmological constant, into his field equations in 1917 to describe the energy of empty space, then famously removed it after Edwin Hubble confirmed the universe was expanding in 1929. After 1998, the cosmological constant was reinstated. But here lies one of the most staggering failures in the history of theoretical physics. When physicists calculate the expected strength of vacuum energy from quantum field theory, the answer they obtain is larger than the observed value of dark energy by approximately 120 orders of magnitude. A 1 followed by 120 zeros. The Nobel Committee's own documentation for the 2011 prize described this discrepancy as the worst theoretical prediction in the history of physics. Quantum mechanics and general relativity, the two most successful and precisely tested theories in all of science, cannot both be correct about this at the same time. The implications extend beyond the present into the far future of everything. If dark energy remains constant or strengthens, the universe will continue accelerating indefinitely. Galaxies outside our local group are already crossing beyond the cosmic horizon. Accelerating away from us faster than light can bridge the gap between us. In the sufficiently distant future, not billions, but trillions of years hence, the acceleration could intensify into a scenario physicists call the Big Rip, the progressive tearing apart of galaxy clusters, then individual galaxies, then solar systems, then planets, then every atom in existence, as the force driving cosmic expansion overwhelms every other force in nature, all the way down to the bonds holding matter together. Dark energy does not top this list because it is the most dramatic object or the most recent discovery. It tops this list because it is real. It is measured. It is confirmed by independent observations from supernovae, the cosmic microwave background, gravitational lensing, and large-scale structure surveys. And our best theories are wrong about it by a factor that has no precedent in the history of human knowledge. We have built every telescope, every particle accelerator, and every equation in physics on frameworks that cannot account for 68% of everything that exists. The universe is not mostly made of things we understand. It is mostly made of something we have never explained, that is tearing everything apart, and that gets stronger every second. If you want to see more videos like this, click the video on screen now and make sure to subscribe.